Hi, this is an AP Chemistry video. We are going to be covering part one of the topic 4.5, which is stoichiometry. So let me get my iPad ready. So stoichiometry is the study of relationships between the relative quantities of the substance taking part in a chemical reaction. So with stoichiometry, we can quantify, how much of a substance will react, how much will be produced, really almost endless different things we can calculate. In order to do stoichiometry, we do need to have a balanced chemical equation because we're going to be using those coefficients and their ratios to be able to convert between different substances within the reaction. So, like I was saying earlier, stoichiometry is useful. It can predict how much products, how much reactants, also how much is left over if we, and we will cover limiting reactants right now, how many moles, how many grams. We can also use stoichiometry of solutions and use molarities, and we can use stoichiometry with gases. This is a mole map to help you to kind of organize your thoughts. I'll just remind you that we use Avogadro's number whenever we're trying to convert between the number of particles and 1 mole or moles. So 1 mole is 6.022 10 to the 23rd particles. So that could be not moles, could be atoms, formula units, molecules, ions. To convert between mass and moles, this is where we use molar mass. So we calculate that or we look it up on the periodic table. Volume of a gas, this is where at STP we can use molar volume. So 1 mole of any gas is going to have a volume of 22.4 liters. And then volume of a solution, this is where we can use molarity as a conversion factor. So all of these are also would be used on the right side of the diagram. To convert between the moles of A and the moles of B, we do a mole-mole ratio. So we would have from the balance equation coefficients, the moles of B over the moles of A. So first thing, just talking again about those mole ratios, we can write many different mole ratios. So this is just an example of the production of ammonia. And you can see that we have 3 moles of hydrogen for every 1 mole of nitrogen. And we could write that as 3 over 1 or 1 over 3 and so on. So we can make ratios between reactants, between reactant and products, or between products. If this one only has 1 product, so we can't do that. So let's do this first example. This is a reaction that produces a compound called cisplatin, which is right here. And this is a possible anti-tumor agent, so like a chemotherapy. What is the mass of the cisplatin that can be produced if we have 100 grams of K2PtCl4? So this is a gram-to-gram stoichiometry problem. They mention the excess ammonia. That means that this is my excess reactant and the one I've been given is my limiting. So what that means is I don't need to do a limiting problem. I don't have to figure out who the limiting reactant is for this one. So if I start the problem with my grams of the K2PtCl4, first thing I want to do is convert to moles. I'm going to use the molar mass that's been given, but it wouldn't be that hard to calculate. So always convert to mole first. Now we're going to use the mole-mole ratio. So there's 1 mole of cisplatin and 1 mole of the K2PtCl4. It is a 1-to-1 mole ratio, but you would still want to show your work. And then lastly, we're going to be figuring out how many grams of the cisplatin. Molar mass is given as 301.1 grams of the cisplatin. Oops, there's a 2 there. For every 1 mole. My writing's getting a little messy. So you can also always cancel out the units. That's why I like to include the substance. So my grams of the K2, PT, Cl4 get canceled, the moles get canceled, then my moles of the cisplatin get canceled, and I end up with grams. So when I calculate this, I get 72.5 grams of the cisplatin. Stoichiometry also involves limiting reactants. Just a reminder, a limiting reactant is the reactant that will run out first. It will stop the reaction from continuing. And then you have an excess reactant or reactants that you will have leftovers of. And so in the container at the end, you'll have the product and then some leftover excess reactant. Theoretical yield is something that we can calculate with stoichiometry. And we will do this oftentimes in the lab because what we do is we're going to compare the theoretical yield, which is based on stoichiometry and the limiting reactant and the math, and then we would compare that to the lab amount that we get, and then we can actually calculate percent yield, which is comparing the actual to the theoretical. The closer to 100%, the better. Here's another problem. We are going to, the question's asking us for what is the excess reactant and how many grams remain after the reaction happens between 4.55 grams of aluminum and 9.62 grams of nickel 2 oxide. So they're not asking us for the limiting reactant here, but you have to calculate the limiting reactant always if you have 2 different reactant amounts that are given. So the first step that I would like you to do is I would always take your amount that you're given. If it's not in mole, convert to mole. So I have 0.169 moles of aluminum. And I like to write that up in my reaction to keep track. And then I have 9.62 grams of nickel 2 oxide. And that gives me 0.129 moles of nickel 2 oxide. So the next thing that you should do once you have both reactants in moles is you're going to take one of the reactants amount in moles and convert it to the other reactant moles. And then you need to evaluate and see whether you have enough. So I'm going to show you both ways. You wouldn't have to do both, but sometimes it's helpful if you're at all in doubt to do both because they should both agree on which one is the limiting. So throughout this video, I will show you both both ways of converting the reactants to each other. So here we go. So I'm going to take my amount of aluminum moles and I'm going to convert it into moles of my other reactant, the nickel 2 oxide. And when I do this, I get 0.254 moles of nickel 2 oxide. So what this is saying is if all 0.169 moles of aluminum react, I would need 0.254 moles of nickel 2 oxide. And you can see that I don't have that. That means this is my limiting reactant and this is my excess reactant. And this amount is not going to be a number that we're going to use at any point later. Let's say by chance you chose the other way. So if I take 0.129 moles of nickel 2 oxide and I convert it into aluminum, I get 0.0 0.0860 moles of aluminum. And again, I evaluate this. So it's saying if I have 0.129 moles of nickel 2 oxide, I need it to react. If I'm going to react all of it, I'm going to also use up 0.0860 moles of aluminum. And you can see that I have plenty of that. So that is my excess reactant. This is my limiting for both of these. So now the question is, what is the excess reactant and how many grams remains? So we know that our nickel 2 oxide is our limiting reactant. So if we hadn't, we would want to convert it to the excess reactant. We just happen to have done that up above, but sometimes you will not have done that and you would have to. So that's how much of the excess reactant that will actually react. So what I do is I take the amount of excess reactant that's given in the question, subtract the amount of excess reactant that reacts, and then that tells me how much excess reactant is left over. So in the question, my excess reactant, I was given 0.169 moles of aluminum, and I just calculated that I'm going to react this much. And then that will give me 0.083 moles of excess aluminum. And sometimes that's enough. In this question, they do want you to go to gram. And by the way, there's many different correct ways to do these problems. This is the way that I teach it. You could have went to grams right away. There's just many different ways. But if I just now take my excess unreacted aluminum moles and then multiply and convert it back to gram, then you can see that I have 2.2 grams of aluminum that are going to be left over in the container. So unless you're going to somehow, capture that, you have this excess that you might, just dispose of. Let's do another problem. So the next problem we're going to do is a solution stoichiometry problem. So in this question, we are given 100 mils of 0.1 molar barium chloride, and it's going to mix with 100 mils of 0.1 molar iron 3 sulfate. How many grams of precipitate are formed? So what we want to do first is, if we're not given the balanced chemical equation for stoichiometry, we have to write it. So for this question, they told me I had barium chloride and iron 3 sulfate. Now it's a double replacement reaction, so the barium is going to go with the sulfate. Barium's +2, sulfate's -2. That is my precipitate. I know that because of my rules of solubility. Oops, I'm starting to balance it and write it at the same time. I'll take out that coefficient. So chlorides are soluble, except for when they're with lead, mercury, or silver. So we know the iron 3 chloride is aqueous. Sulfates are insoluble with calcium, strontium, and barium. So these are also aqueous. We're not doing a complete or net ionic equation here, but it's good to know. So then I would definitely want to balance this. And you can see that I have 2 irons on both sides. I have 6 chlorines, 3 bariums. I would want to put a 3 here. So now it's similar to what I've just been doing. I do need to determine who the limiting reactant is before I can determine the amount of the precip. Precip is this one, but before we do any of that, I'm going to take my amounts of my 2 reactants, so my 100 mils, I'm going to convert that into liters. You don't have to show this step if you don't want to. And then I'm going to use the 0.1 molarity is the same as that many moles of barium chloride in 1 liter. So when I do that, I get 0.0100 moles of barium chloride. And by the way, this one, I think a lot of people, you could probably see which one is limiting without doing the calculation. That's fine as long as you explain your reasoning. But I'm going to continue. So I'm given 100 mils. Again, I have to go to liter of the 0.1 molar iron 3 sulfate. So I also have 0.0100 moles of iron 3 sulfate. So you can see based on the mole ratio which one is the limiting, but I am going to show you just because it's a process. So first thing I did is I always convert to moles, my reactants to moles. Second thing now is I'm going to determine the limiting reactant. So I am going to take my moles of barium chloride and convert that into moles of iron 3 sulfate. And when I do that, I get 0.00333 moles of iron 3 sulfate. So do I have enough of this? My answer is yes, which tells me this is the excess reactant. This is my limiting reactant. But I could also have chosen the other way. And like I said, this one you can actually reason based on the coefficients too. But if I were to take my 0.0100 moles of iron 3 sulfate and convert that into moles of barium chloride, you're going to get 0.0300 moles of barium chloride. And you could ask yourself, do I have that? My answer is no. So that means the barium chloride is my limiting and the iron 3 sulfate is my excess. And remember, I think it's a good idea to put a line through that because you're not going to use that number. So then the question is asking me how many grams of precipitate. So now that I know who the limiting reactant is, which I'm going to start with, the barium chloride. And now my precipitate, remember up above, was the barium sulfate. And then I just want to go to grams by using the molar mass of the barium sulfate. And when I do that, I get 2.33 grams of the precipitate, the barium sulfate.